Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last session, we learned about two binary codes BCD and XS3 code. In this class, we deal with gray code and alphanumeric codes. Let us start with gray code. The gray code is an unweighted code. What does it mean? As I told you in the last lecture, no positional weights are associated with the digits of this binary code. One more point to be noted is that it is not an arithmetic code. The very special characteristic of gray code that makes itself popular in data communication applications is that it is a unit distance code, which means that only a single bit is changed from one code word to the next in the sequence. Due to this special feature, it is also known as cyclic code. Consider an example. The gray code for the decimal number 5 is 0111 and for 6 it is 0101. When we examine these two adjacent codes, we can see that they differ by only one bit position, that is the third bit from left. One is changed to 0. The same is the case between any two adjacent gray codes. This feature makes it prominent in such applications where the chance of occurring errors increases as the number of change of bits in adjacent codes increases. Consider a case of transition from one number to the next. If binary numbers are used, a transition from 0111 to 1000 may produce an erroneous number 1001. How? If the transition of the last bit is delayed, the number becomes 1001. This problem is eliminated if we use gray code, because it just need to change only a single bit. Such transitional errors are reduced while using gray code, and if more than one bit variation is detected, that is noise. So, error detection becomes easier. Let me introduce one more important characteristic of gray code. It is a self-reflecting code. I will explain this. As in the case of binary numbers, gray code can also have n bits representation. One bit gray code has two code words 0 and 1 representing decimal numbers 0 and 1. Gray codes for n plus 1 bit numbers can be constructed from n bit codes. To obtain the n plus 1 bit representation, we write the n bit codes twice, one set below the other, with the second set in the reverse order like mirror image. Obviously, this is the reason we use self-reflecting code. Then add 0 at the beginning of the first set and 1 at the beginning of the second set. Now, to generate 2-bit gray code representation, write 1-bit representation twice, 0, 1 first set, then in the reverse order 1, 0 below to that. Then add leading 0 to the first set and leading 1 to the next. Then we get 0, 0, 0, 1, 1, 1, 1, 0. Here we have constructed the 2-bit gray codes. You can glance through the numbers and verify the single bit change. This can be extended up to any n-bit gray code. So, to obtain 3-bit code, we write 2-bit code twice with the set below in reverse order. Here comes the reflection. Add leading 0 to the first set and leading 1 to the next. Then we get the 3-bit codes starts from 0, 0, 0 and ends at 1, 0, 0. Hope it is clear. Now, let us have an illustration of how gray code is used to solve erroneous results. Suppose that we would like to measure the rotation of a spinning disk using a set of sensors. and we need to know the disk position at any instant of time. The disk is of circular pattern. So, if we consider 45-degree partitions, there will be 8 radial sectors. Imagine that the number of each sector is encoded on the disk and it can be read by 3 sensors, each digit by a sensor. Let us take 3-bit representation. If the numbers are encoded in binary, each sector will have a code from 000 to 111 in sequence. Okay. As the disk starts spinning, the sensors start reading the numbers. When the first sector comes, it displays 000, for the next 001, etc. and at last, for the last it produces 111. So, we are able to get the disk position at any moment. It works well, good. But think of a moment where the disk is on half the way from 111 to 000. Sector 111 is moving out from the visibility and sector 000 is about to enter to the scope of the sensor. Transition of 3 bits is to be taken place, but it may so happen that the sensor produces a delayed result. So, it may generate a value 011 which is erroneous. So, we have to think of an alternate code. What is the advantage of using gray code here? Let the sectors are encoded with gray code in sequence. Then each 45-degree rotation or transition of a sector to the adjacent sector brings only a single bit change. If a transition from sector 111 to 101 occurs, note that 111 and 101 are adjacent numbers in gray code, and even the sensor is delayed, it produces either 111 or 101 because only a single bit has to be changed. Either the bit changes or it does not change. The only possible outputs are 111 or 101. It will not leave the system with a wrong result. When we deal with digital circuit designing, many times we have to do conversion between binary and gray code. So, next we move on to conversions. First one, binary to gray code conversion. Take a binary number and convert it into its gray code equivalent. For that, let Bn minus 1, Bn minus 2, etc. B naught be a binary number and Gn minus 1, Gn minus 2, etc. G naught be its gray code equivalent. Then to obtain Gn minus 1, Gn minus 2, etc. G naught, we can follow a procedure. Write down the most significant bit of binary number as it is, because the most significant bit of the gray code is always equal to the MSB of the given binary code. Then the bit next to the MSB of the gray code, that is Gn minus 2, is equal to the modulo 2 sum of Bn minus 1 and Bn minus 2. All other lower order bits can be obtained using the same mechanism. For example, let us convert the binary number 11001 to gray code. So, we write the binary code 11001, write the MSB B4 as it is in the position of G4. So, G4 equal to 1. Next, to obtain G3, perform modulo 2 addition on B4 and B3. Modulo 2 sum is the sum of 2 bits discarding the carry. Okay. Then we get 1 plus 1 equal to 0. The next bit G2 is obtained by adding B3 and B2. 1 plus 0 equal to 1. Add B2 and B1 to obtain G1. At last, B1 plus B0, that is 0 plus 1 equal to 1, that is G0. So, the gray code equivalent of 11001 is 10101. We shall do one more problem. Convert 11101 to gray code. MSB is the same. Then 1 plus 1 equal to 0, 1 plus 1 equal to 0, 1 plus 0 equal to 1 and 0 plus 1 equal to 1. Then we get the final answer as 10011. Next, we are going to convert a gray code to binary, gray to binary conversion. The rules are slightly different. MSB we write as it is. To obtain Bn minus 2, we calculate the modulo 2 sum of Bn minus 1 and Gn minus 2. The most significant bit of the binary is always equal to MSB of the given gray code. The bit next to the MSB of the binary, that is Bn minus 2, is equal to the modulo 2 sum of Bn minus 1 and Gn minus 2. All other lower order bits can be obtained using the same mechanism. Consider the gray code representation 01101. We have to convert it to binary. As per the rules, B4 equal to G4. Then B3 equal to B4 plus G3, that is 0 plus 1 equal to 1. Then B2 equal to B3 plus G2, that is 1 plus 1 equal to 0. Then B1 equal to B2 plus G1, that is 0 plus 0 equal to 0. Then B0 equal to B1 plus G0, which is equal to 0 plus 1 equals 1. So, finally, we get the answer 0, 1, 0, 0, 1. You can try out more examples by yourself. So, we have come to an end of the discussion on gray codes. To communicate, we need not only numbers, many other characters and symbols are required. Alphabets, numbers, special characters such as plus, minus, hash, percentage, etc. To represent all those characters, we use another set of codes called as alphanumeric codes. That is the topic we are going to talk next, alphanumeric codes. Alphanumeric codes are binary codes that represent alphanumeric data, which includes alphabets, numerals and special symbols and special characters. For representing an alphanumeric data, we need codes for at least 26 alphabets and 10 decimal digits, a total of 36 at the minimum. Then we have to go for a 6-bit binary code representation, because using 5 bits maximum of 32, that is 2 raised to 5, 32 codes can only be generated. So, we move to 6 bits representation with 64 binary combinations. 36 binary combinations are already used for alphabets and numbers. The remaining 28 are available for other purposes. Symbols other than numbers and letters or some control information can be coded using these combinations. As we use more number of bits, more characters can be encoded. The next, ASCII. One of the most widely used universally accepted alphanumeric code is ASCII, American Standard Code for Information Interchange. It is very popular in data communication applications. Many keyboards use ASCII to convert characters to binary codes. ASCII of two types, ASCII 7 and ASCII 8. ASCII 7 uses 7 bits to represent a character. 128, that is 2 raised to 7 characters can be represented using ASCII 7. In the same way, 256 different characters can be represented using 8-bit ASCII. Actually, ASCII 8 is an extension of ASCII 7. The additional bit is added to the left of ASCII 7 codes. The 128 characters of ASCII 7 are used as it is in ASCII 8 to make them compatible each other. The table given here lists the ASCII code in decimal, binary and hexadecimal representations. Let us refer this table and express a word or a statement in ASCII. For example, write the ASCII code of the word hello. From the table, we write the binary equivalents. Also, you can write the hexadecimal equivalent. The character H takes a binary value 1001000 and hexadecimal value 48. Character E takes binary value 1100101 and hexadecimal value 65. Then character L in binary is 110110 and its hexadecimal representation is 6C. Then we have two L characters. Then character O is represented in binary as 1101111 and in hexadecimal 6F, and exclamation mark it is 0100001 and in hexadecimal 21. So, the string hello can be encoded as 48656C6C6F21 in hexadecimal, and the corresponding binary can be seen here. This is how we determine the sequence of ASCII codes. Each character takes 1 byte memory. Next, we go for another important alphanumeric code, Unicode. It is a universal text character encoding scheme. Computer is a machine that connects people all around the world. Many of our manual activities are replaced by digital devices. Each one wants to interact with the devices in their own local languages. But how do we represent all those numerous number of characters and symbols used in different languages? The different coding schemes, including ASCII, did not have adequate number of bits to satisfy the need. Several new coding schemes were introduced on this context, but none of them served the purpose completely, because in many of the cases the number of bits were not adequate to represent all characters. And another limitation was the conflict between different encoding schemes. As each coding scheme was developed independently, it happened that the same characters were encoded differently in different languages. So, communication between systems that use different coding schemes was difficult. As a result, we were not able to transfer data and files internationally. To overcome these limitations, the Unicode standard was designed. This encoding system provides a unique code for every character irrespective of the language, program or the platform. This makes the data communication around the world efficient and reliable. So, it is considered as universal character encoding standard. One of the major advantages of Unicode is that it provides the simplicity and consistency of the popular ASCII code. The bit values of ASCII representation of a particular character is maintained in Unicode scheme too. Hence, Unicode becomes convenient and backward compatible with the existing systems that use ASCII. It is an expansive multilingual character encoding standard. Also has a capacity to encode millions of characters. The Unicode standard managed by the Unicode Consortium defines nearly 1,50,000 characters covering around 150 modern and historic scripts, symbols and other controlling and formatting codes. Next, let us look into the different encoding forms defined by the Unicode standard. It has several character encoding forms. The first one is UTF-7, the Unicode Transformation Format 7. It uses 7 bits for each character. It was designed to represent ASCII characters in email messages that required Unicode encoding. The next, UTF-8. It is a byte oriented format. It is the most popular type of Unicode encoding. It only uses 1 byte, that is 8 bits, to encode English characters. It uses 1 byte for standard English letters and symbols, 2 bytes for additional Latin and Middle Eastern characters, and 3 bytes for Asian characters. Additional characters can be represented using 4 bytes. As the first 128 characters are mapped with ASCII, UTF-8 is backward compatible with ASCII. Another encoding form is UTF-16. It is a word oriented format. Here we consider one word as 16 bits. It uses 2 bytes, that is 16 bits to encode most commonly used characters. If needed, the additional characters can be represented by a pair of 16-bit numbers. However, UTF-16 supports 4 bytes for additional characters up to 1 million. The next encoding form is UTF-32. It is a double word oriented format. Each character is encoded with a fixed length of 2 words. This is useful in environments where memory is not a concern, but fixed width access is desired. Unicode supports numerous scripts used by languages around the world and many technical symbols and special characters used in publishing. Currently, Unicode can represent most of the characters in use around the world, and it gets updated day by day to make it more complete. A part of the code space is reserved in Unicode standard. It is for the users to set codes for their own symbols and characters. There are many other alphanumeric codes, but these are the popularly used ones. Let me summarize the topics we discussed. Gray code is an unweighted cyclic code. It cannot be used for any arithmetic operations, but they are widely used to facilitate error correction in digital communications. The most attracting feature of gray code is that the adjacent codes differ in just a single bit. We can convert binary to gray code and the reverse, gray code to binary. Basically, binary is changed to its corresponding gray equivalent in order to reduce the switching operations. Transition from one code to the adjacent code requires change of only one bit to another, which reduces the number of switching operations considerably. Then we talked about alphanumeric codes, ASCII and Unicode. ASCII is a very popular 7-bit or 8-bit code which can represent maximum of 256 characters. The Unicode standard is the universal character representation standard, and it provides a consistent way of encoding text of several languages, which helps in exchanging files internationally. Let me wind up. Let us meet in the next session with a new topic, error detection and correction codes. Thank you for watching. Bye.